In this video, we're going to look at trigonometric identities. So let's recall some of the fundamental identities we've already seen in prior sections. The first few are our reciprocal identities. These are the ones that look at how one function relates to another in terms of reciprocals. So cosecant of x equaling 1 over sine of x, secant of x equaling 1 over cosine of x, cotangent equaling 1 over tangent, and then we have the tangent and cotangent functions defined in terms of sines and cosines. The next set of properties we have are the Pythagorean identities, and again these are the ones that relate our trig functions to the real number 1 using the unit circle. So sine squared of x plus cosine squared of x equaling 1. Again, that's the one that you really want to remember. The others we can derive from that. So if I divide out by cosine squared, we get the tangent squared x plus 1 equaling the secant squared x. And if we take the sine plus cosine equaling 1 and divide out by sine squared, we get 1 plus the cotangent squared is equal to the cosecant squared. Some other identities that we've used throughout this course so far are the even and odd identities. So these are the ones that tell us where how our graph reflects about the y-axis. So if I'm looking at sine of negative x, that's going to give me the negative sine of x. Cosine of negative x is equal to cosine of x. And tangent of negative x equals negative tangent of x. So this tells us that cosine is our only even function. Sine and tangent are both odd functions. And then lastly we have our cofunction identities. These are the identities that give us corresponding shifts between the different functions. So looking at sine, if I take pi over 2 minus x as my angle, then I'm shifting and I end up with my cosine graph. If I look at tangent and shift it by pi over 2, I get my cotangent graph. And for secant, if I shift it, I get my cosecant graph. Now all of these identities are ones that we're going to need in order to do more things, especially solve equations with trig functions. So one of the first things you're going to be asked to do is to prove what we call trigonometric identities. And by proving trigonometric identities, it just basically means we're going to look at making sure that one side of the equal sign is equivalent to the other. Many trig identities and formulas come from the fundamental identities that we just talked about. One of the things you'll need to be able to do is verify that a given equation is an identity. And again, an identity versus an equation is true for certain values, an identity is true for all values. Okay. So the trickiest part of this is that you will want to solve the equation, and this is not what you want to do. Okay. When we are given an equation and asked to solve, we're looking for that one value that makes sense in the equation. When we're looking at an identity, we are actually trying to show that two sides are equivalent, and so we can't always use the same operations. Many of the operations that we use in solving equations are not reversible. So we have to make sure that what we're really rewriting one side of the equation to be identical to the other side. Some examples. If I'm looking at multiplication, there is a reversible operation, and that's division. If I'm looking at subtraction, the reversible operation is addition. But some of those operations, as I said, are not reversible. So things like squaring and square rooting. It almost seems reversible, but in one case I'm going to get one solution, in another case I get more than one. And so it does make a difference when I do those operations. So steps for proving trig identities. Okay. The first thing we're going to want to do is start with one side of the equation. Sometimes this will be indicated for you. Okay. You're only going to want to work one side, because if you start working both sides of the equation, you may lose the fact that you are proving an identity and end up solving. Okay. So the idea is to rewrite the side to look like the other side. And how we're going to do that is in step 2. We're going to use some of the fundamental identities, use algebra, and the identities you know to rewrite expressions. So for example, I can multiply by forms of 1, so things like x plus 2 over x plus 2. I can rationalize denominators or numerators. We can get common denominators. All of those things are properties that we've used before to rewrite expressions. And then lastly, convert to sines and cosines. In some cases, you may not be able to use some of those properties to rewrite functions. And so in that case, you want to just take it back to basic trig functions to make it easier to simplify or rewrite. So let's look at a couple of examples. We want to verify the identities by transforming the left side of the equation. And again, in some cases, you may be asked to do the right side or pick your own side. But you're always going to want to start with one side or the other. So here we're going to start with the left side. So cosecant of x minus sine of x is equal to cotangent x divided by secant x. And we want to transform the left side to look like the right side. So again, the first thing we're going to do is start by rewriting the equations. Now in this case, if I'm looking at my right side, I know exactly what I'm trying to get to, cotangent over secant. And if I think in terms of those are basically sines and cosines. So I'm going to start by rewriting my left side in terms of sines and cosines. So here we use our reciprocal identity. Now I'm going to use an operation to simplify this. I'm just going to get this to a single fraction by using a common denominator. And then we can use our Pythagorean identity to rewrite the top. Now if we look at this, this is not quite where we want to be, but we can use what we've now found to rewrite the expression. So if I look at cosine squared over sine x, I can think of this as cosine of x times the cosine over the sine. And though cosine is a nice trig function, again our right side doesn't have any cosines, so I can rewrite that using the reciprocal identity. And we'll notice that cosine over sine is also one of our reciprocal identities. Okay, let's look at another example. So we have the quantity 1 minus cosine squared of x times the quantity 1 plus cotangent squared of x equal to 1. We want to rewrite the left side of this equation to look like the right side. So in other words, we want to verify that the left side is equivalent to 1. Okay. Well, because of the squares in the parentheses, these are begging to use the Pythagorean identities. So 1 minus cosine squared we know is sine squared, and again 1 plus cotangent squared is our cosecant squared. From there we can use the reciprocal identity. So cosecant squared is 1 over sine squared, and we can see when we multiply these together, sine squared times 1 over sine squared, we get our value of 1. In this next example, sine of theta divided by 1 plus cosine of theta, we want to be equivalent to 1 minus cosine theta divided by sine theta. Okay. So again, we're going to take the left-hand side and we're going to start by rewriting. Now in this case, sine over 1 plus cosine does not match any of our properties, and it's already in terms of sines and cosines. So here's where we want to multiply by a form of 1 to rewrite the expression. And just like with most things, if I'm going to multiply by a form of 1, I usually want to conjugate whatever's in the denominator. So we're going to multiply by 1 minus cosine theta divided by 1 minus cosine theta. Now doing this, when we multiply out, we can see that on the bottom I have a difference of squares. And again, we can use our Pythagorean identity for the 1 minus cosine squared. From there we can see that sine squared and sine theta, we can cancel one of those, and we've now reached the right-hand side of the equation. In the next example, 1 over secant x plus tangent x plus 1 over secant x minus tangent x equals 2 secant x. So here again, we want to take the left-hand side and turn it into a secant. Now, because I only have one term on the right side of the equation, the two terms I definitely want to start by combining. So we're just going to get a common denominator and simplify that to a single fractional expression. Now we just want to combine like terms. So on the top we can see that the tangent x's will cancel out, and on the bottom we can see we are going to get a difference of squares. And notice again on the bottom here, this is again one of our Pythagorean identities. Secant squared x minus tangent squared x is just 1. So this is just going to simplify to 2 secant of x. In our next example, tangent x plus cotangent x squared is going to equal secant x plus cosecant x. So here again, left-hand side, we have a quantity squared. So just like normal, we probably want to start by expanding that. So the first thing to notice in this expression is that tangent x times cotangent x, well, those are reciprocals of each other, so those multiplied together will just give us 1. And our tangent squared and cotangent squared, we can use our Pythagorean identities. Now these are not the same Pythagorean identities, so we're just going to rewrite them with their corresponding expressions. And now if we look at what's left over, minus 1 plus 2 minus 1, those will cancel out. And so we're just left with secant squared x plus cosecant squared x. In our last example, tangent of x plus tangent of y divided by cotangent x plus cotangent y, we want to equal tangent x times tangent y. Now in this case, if I'm looking at the right-hand side, I'm only in terms of tangent. So the first thing I'd probably want to do here is get everything in terms of tangent. Okay? There are many ways to start this. Some of them will make this longer than others. But here, if I notice using the reciprocal identity first, it's going to simplify some of the things that I have to do. And so here you have to be a little careful how you reuse that reciprocal identity. Remember, it doesn't just put 1 over the tangent plus x plus tangent y. You have to separate that into 2 separate terms. From there, we're going to get a common denominator in the denominator. And from there, we have a complex fraction. So the tan x plus tan y divided by tan x tan y in the denominator, we're going to invert and multiply, and then we can simplify the expression. So here we can see when we multiply, the denominator and the tan x plus tan y will cancel, and we're just left with tan x times tan y. This section of the course you are definitely going to want to practice and practice and practice. Each of your identities that you are trying to verify are going to be different, and it's going to depend completely on the types of functions that are present as to what the operations are that you're going to want to do.